we've done this. We've done sampling variability. We've talked about p-hat. I unintentionally got us into the world of x-bar the other day. That's what we're covering today. If we do central limit theorem tomorrow, which is Thursday, then Friday I want a frappy 2 euro my nerves. I have no patience today. It's all gone. Friday I want a frappy, but I don't want a Monday test. I want to wait to test on Tuesday. Literally, my logic is just because I have a doctor's appointment, so there's going to be a sub anyway, so might as well. So on Monday, we'll probably start Chapter 8 notes, but the Chapter 7 test won't happen until Tuesday. Everyone cool with that?
Mm-hmm.
Yes, dear.
So is the sub going to be on Monday or Tuesday?
Tuesday.
Okay.
That's why we're going to do the test Tuesday, since I'm not here, and y'all can just knock it on out without me. It'll be fine. Now, we might could get a head start on it on Monday, depending on how quickly we can get through the notes, but we'll put the test on Tuesday. Now, I was supposed to be out Friday, but my conference has been canceled, so this all will work out well, so that's good. Yay, fun times.
So, question about
Yes.
how many did you say?
We reduced it and said, did we say 5? I thought we said 4.
It was 5.
I think it was 5. No, he's right. He's right.
So, what about the first one that has
No, that one only has 3, so you have to do all 3. But like on this one, you could do 1, 2, 3, 4, 5, and not do 17, 19. You just have to pick 5. So total, there should be 5, 10, 15, 23. So it's out of 23. So if you do more than 23 problems, you're getting more than 23 points. I'm not that dumb. I know when problems have multiple parts. If you think I count those as individuals, I don't. If 25 had 3 parts, it's still just 25. Just FYI. 25 is not even a number assigned. That's funny. Okay. So, I do want to talk about sampling distribution of X-bar today, which unintentionally we veered into that world 2 days ago because, like I was telling Louise, and in the calculus people were understanding, the algebra 2 trig people will understand too. It's just any math class. When you get to the end and you know all the things, it's hard to pretend you're back at the beginning and you didn't know any of the things. So that's my problem with stats at the moment, is I know the end of Chapter 8 and how this all wraps up in a nice pretty bow. So here we are in the middle of Chapter 7 and I keep trying to bow it and it's not time to put the bow on it yet. So that's my bad. Okay, we got this handout the other day. I don't even want to ask, do you still have it? I feel like I'll have major regrets with that question. If you still had this handout, it is very useful. And I'm going to reference it now. You and I have been dealing with sampling distributions. And lately we've been talking about p-hat. And today we're going to talk about x-bar. Does anyone know the difference between p-hat and x-bar? P-hat is dealing with...
Population. X is
P is population, so p-hat's got to do something with that. And then x-bar is going to do...
P-hat the mean of the population, and then x-bar is the mean of the sample.
P-hat's proportions.
I look at my notes, so,
When I see p-hat, we're wanting proportions. We're wanting a percentage, we're wanting to smack something like that on it. Whereas x-bar is dealing with
The mean of the sample.
the means.
Yeah.
So, I mean, I could be very, very specific, like my learning target is, and say sample means x-bar, or sample proportions, p-hat. So it's all from the samples. And again, we've taken multiple samples. That way we can have a sampling distribution. But regardless, sometimes we're wanting to talk about the means, and sometimes we're wanting to talk about the proportions. Yes, dear?
What is the 10% condition?
That's the NP greater than 0.10.
That thing you
I thought that was the thing of large numbers.
Yeah, and it's some call it the 10%, some call it the law of large numbers. I'm going to start calling it 10% just so I keep remembering it's 0.10. Honestly, that's my logic. Because we're going to talk about the central limit theorem tomorrow, which involves a specific large number, and then it's like, oh my gosh, too many things all in the brain. Okay, so we've been dealing with this, and I kind of like the steps that they show. It's just, I think it's out of order. Again, any problem I get, the first thing I check is that we're greater than 10. I check this first. And then after I check that, yes, I can calculate that standard deviation. And if I check this, I'm able to assume normality. And if I'm able to assume normality, I'm able to put it on a normal curve, which means I can then do a z-score. And then I can then stout some sort of specific percentage at you, like 89% of samples of this size will fall between this and this.
Ms. Cochran,
Yes, dear.
is the next page of these notes supposed to be 6.3?
No, we're going to talk about that.
Okay.
That was, well, I had good intentions, but we're going to let it go. We're going to be like Elton. Okay, so what we've done is dealing with proportions. What we're going to talk about today is properties of sampling distribution X bars. They're not really that, they are different. They are different. Anyway, so we're back on the notes, but this is going to be helpful, and we'll talk about this one tomorrow. Notice that there is an extra thing in here that involves something called the central limit theorem, but that's tomorrow's problem. Okay, so let's go to our notes. We're on the 7.3 page. I really should have done this page 2 days ago instead of trying to do that word problem. If we're being honest. It's like the word problem made life worse. And Louise is asking about the page after this, the binomial and geometric. We hit binomial right before Christmas. That was the around the room thing you liked. Binomial was good. We never even talked about geometric. And then if you recall that last test, it really didn't have much binomial on it anyway. So I intended to go over binomial and geometric again at this time. I don't think it's going to happen because I need us to move on to chapter 8, so we'll have to find another time in life to review that. So that's why there's some random chapter 6 stuff at the end, because I thought we needed to go over it again, and we do, just not now. Okay, X bar, sampling of means. We only have one practice problem. We have a lot of words to read first, sadly enough. And it says, the mean of the sampling distribution of a sample mean. We're assuming if we took a sample, remember we're taking lots of samples, like an X1, an X2 bar, an X3 bar. That's the mean of multiple samples. And then we were to plot all these points and make us a curve where well, then I got off center when I drew the line. Good times. Then where that mean actually happens would be the mean of our population, we pray. Hence this notation. Hopefully the mean of our multiple samples, where we find it if we were to plot them on a histogram like this and apply a bell curve, that mean is the mean of our population. Okay, so depending on the problem, we have to decide, is it a sample proportions problem or is it a sample mean problem? Ms. Compton is used to doing both, so didn't think about it the other day. So you've actually already worked a sample mean problem, because we used this formula 2 days ago. When we did, it was problem 1 on that other page. The one that says like day 3 at the bottom. And we talked about those train cars carrying the bauxite ore.
Mm-hmm.
That was a sample means problem. So literally it's going to end up being a lot of the same steps. We're still going to want to apply a z-score. We're still going to want to do a lot of the same stuff. It's just one tiny bit of a difference is the fact that we use this formula, which is why Louise kept questioning me, and I was like, there's a reason Louise is questioning me, and here's why.
Wait, so that's the standard deviation formula for the sample?
Yes.
Oh, me.
It is the standard deviation of the sampling distribution of the sample mean. So it's the standard deviation of the sample mean. The standard deviation of all these points then.
Yeah, I get that, but I thought, like, on the formula sheet, I thought it said it from you.
It's the formula sheet. I just was looking at it. Formula sheet. Where did you go? Not my formula sheet.
I want to say mu, but it says it equals sample mean.
Someone got a formula sheet handy?
Yeah, I have one right here.
Oh, I got mine. Yay. Your normal formula sheet, the one you're allowed to hold on to all year. Oh. We talked about this the other day, that we have been doing this formula. Well, no duh, we've been doing that formula because we've been doing proportions problems. Then the problem we did 2 days ago, Louise was like, why the crap Miss Compton are using this formula now? And the reason the crap Miss Compton was using that formula now is because it was a means problem. Miss Compton needed to pay more attention to context. Is it a proportions problem or a means problem? If it's a means problem, use this formula. If it's proportions, use that one.
So that's a type of statistic, but that is going to be okay. I
Yes.
got it now. That
Yes.
makes sense now.
Yes. Okay. I don't know if that made sense to you, but basically, Louise has finally made peace with 2 days ago. That's what me and Louise are discussing now. Okay.
Stupid question.
Okay.
How do you know if it's a mean problem or?
We're gonna go over that, and we're gonna look through them and like call them out. Like this one would be a this one would be a that. No, not at all. Clearly not. I treated the other one the other. I mean, I would treat it. Did we end up doing the same steps? Could you still follow? Yes. But do I need to know which of these formulas to use? Yeah. Okay. We still check what I'm going to start calling it the 10% condition, law of large numbers, whatever you want to call it. We still want to know that NP greater than or equal to 10, or N times 1 minus P greater than or equal to 10. We still want to know that. We're still checking that NP part. Okay, now there is a little bit difference between X bar and P hat in this. So P hat is great. And P hat, if we're able to prove this, we assume we're on a normal curve, and then we're able to do the z-score and say fun math things after that and go back to our chapter 2 ways. X bar is even cooler than that. It's much like that of the sample proportion. So it's a lot like P hat, except the sample mean is an unbiased estimator of the population mu. That, I guess we could have guessed that. It's supposed to be unbiased. Whatever, that's fine. The values of X bar are less spread out for larger samples. Their standard deviation decreases at the rate of 1 over square root of n. That's kind of how they came up with this formula here. And you should only take this formula when the population is at least 10 times larger than the sample. So in the past, I don't think we really focused on if the population as a whole being 10 times larger than the sample. We mentioned it at the beginning of the chapter 7 notes, but we actually have to check it now. In order to use this formula, we need to prove our population is 10 times larger than our sample. So if our sample is 4, our population is going to be 40 or higher. Okay. Here's the really cool thing. So with P hat, we have to show that NP greater than or equal to 10, and if it's not, then we stop and we say, I'm sorry, I can't apply abnormality. That actually doesn't happen with X bar. With X bar, even if we fail to show that we're from a normal population, we can still work the problem. And that's what tomorrow we're going to talk about. There's a theorem that lets us apply it. If we take enough samples, no matter what, the samples are going to make a normal curve, even if they're coming from skewed data. So we talked the other day about, I'm always on IQ, so let me get off IQ for a second. People's income would be good. The income of people in the United States is clearly going to be skewed because some people make a ridiculous crap ton of money, and that's nowhere near the normal average. But if we took enough samples, the samples, and we put all the little X bars on their own graph, they would end up being a normal curve. So just because your population is not normal doesn't mean the sampling distribution of X bars is going to be not normal. I know that seems fishy. You're like, if this one's skewed, shouldn't this one be skewed? But actually, no, it doesn't end up being that way. And that's due to this central limit theorem, which is tomorrow's problem. Okay, so let's just look at the exercise at the bottom. So Ms. Compton's not just saying words at you. And let's see what it says. It says the height of all young women follows a normal distribution. So they told us to begin with normal distribution. So we don't have to check the NP thing because it told us straight up it's normal. It's got a mean of 64.5 and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5. Show your work. Find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5. Show your work. And comment on the differences in your answers. Okay. So, we know. Did that earlier. Perfect. Part A. Find the probability that a randomly selected woman is taller than 66.5. So Kinsey asked, how do we know this is a means problem, a sample means problem? Key things that they tell us. Seriously, it's all got to do with what did they tell you. They told us the mean. They told us the standard deviation. If we were to look at our problem, we worked the other day with so if you have out your other stuff, and we worked that problem with the hobbits. If you look at the hobbit problem, they didn't tell us the mean. They didn't tell us the standard deviation. They only told us proportions. That's why it was a sample proportion problem. Literally, I just look at the problem itself. What information did they give me? If you look at the given information, and they're giving you means and standard deviation, it's a sample means problem. If they're giving you proportions, you need p hat. If they're giving you means and standard deviations, you need x bar. Literally that easy. So I don't know why 2 days ago it didn't dawn on me. We had a problem where they didn't say any sort of proportion, and they gave us a mean and a standard deviation. Why I thought y'all would just roll with it and not ask questions, I don't know. I guess I just, again, I know the bow at the top. If I could just draft the package and call it a day, I would. Okay, so part A, find the probability that a random selected young woman is taller than 66.5. Show your work. Okay. Are we able to do this? So we're wanting to show that she's how tall?
66.5 or taller.
Okay, so I'm going to change that to a z-score because I am who I am. I cannot change who I am. So I'm going to do 66.5 minus the average of 64.5, and I'm going to divide it by that standard deviation, which is 2.5. And when I do that, I end up getting z is 0.80. Now, the reason I'm able to do the z-score, why am I okay with immediately starting and doing the z-score in this problem?
Because it says normal distribution.
Specifically in the stem, it said normal. That's the only reason I can automatically start off with I'm going to apply a z-score. Otherwise, I would start trying to check things and make sure we can actually assume normality. Okay, so I'm going to do the probability of z being greater than 0.80. And I'm going to look at my z table because I am who I am. But Hunter's not going to do that. Instead, he's going to, in his calculator, press
Check and bars.
and then normal CDF.
And then like one check.
And then, so I'm going to draw me a picture.
Check.
We don't want to know when it's higher than 0.80. So he's going to set his lower at 0.80. He could set his upper at something with a bunch of ones. He could do his mean of 1 and his mean of 0 and his standard deviation of 1 if he's doing the z-score way, or if he was too lazy to turn it into z-scores.
Exactly correct.
That's fine. If he was going to do that, he's using the standard deviation given, he's using the mean given.
Lower set to 66.5 and upper just one with a bunch of zeros.
Doesn't matter which one, you're going to get the same answer either way. I'm going to get the same answer with the z table. Maybe off a decimal place, like a hundredth of a decimal place, maybe. I like the z-score because when I see 0.80 and I see how little far away that is from the mean, that helps me realize this should be a really large number in my mind. Or a really small number. You know, like I in my mind, the z-score helps me think about how much area is under that normal curve. And I think it shows you understood it was a normal distribution to go to a z-score. But since you're applying this and press normal CDF, I guess you're already assuming normality anyway. So as long as you've either referenced that the stem said normal distribution or you somehow checked for normal distribution, it's okay if you're lazy and just do his way. Again, old school stats people, I know I'm not that old school and calculators are around, but when I took stats class, we weren't cool enough to get to use calculators. I had to know by hand how to do this with my z-table. And they might always ask me multiple choice question from the z-table. So Hunter still knows how to read it, even though he rarely uses it. I got 21 point something. I got 1 minus 0.7881, which is 0.2119 when I did it earlier.
Miss Compton?
Yes, ma'am.
Was Brittany Canada in 6th period today?
Yes, ma'am.
She was not?
Yes, ma'am, she was.
She was? Okay, thank you.
Oh, Brittany.
Yeah, that's a good question.
Oh, Brittany. Say what now?
Where's all your calculus?
Oh, they're the algebra 2 trig can't graph right now,
Oh.
so I had to take them.
Sure.
It's the chapter where you're supposed to know how to the general shape of like a cubic or the general shape of a quartic, and so therefore if they had a calculator they could just cheat. So all the calculators are they just buzzed and asked about you, baby. You better go get that cleared up. Okay. Thank you, dear. Okay. And now I need to put words because it says stats class. It said show my work. I showed my work. I got 0.2119. That's great. I need to put some words with it. So the probability of choosing a young woman. At random. And then what else do I need to add about her? Whose height. I'm going to throw their exact words at them. Exceeds 66.5. 66.5 inches. Is about 21%. I have an answer.
Why do we know that just because it's greater than 10% that instantly makes it normalized? I mean, I get that kind of makes sense because, it's such a large, size that, it makes sense for it to be normal.
Since it said normal in the problem, we're rolling with it.
No, I mean, like, in general, if it were larger, just because it's larger than 10%, how do we know that makes it normal?
Thankfully, I question it with p hat, but with x bar, thankfully we have what we're about to get to, which is called the central limit theorem. And basically, as long as our sample size is bigger than 30, we're going to assume everything's normal anyway. So as long as we're doing, as long as n is bigger than 30, we're going to assume it's normal anyway.
Why is that? How are you going to get that?
It's, I meant to do it. I can show you, hold on. Well, I could show you. There's an applet I could show you. Where are you? I was just too lazy. No, like a. Come on, where are you? Let's do 2000. Here, I'll show you under the screen, but I was going to show you tomorrow when I actually do the central limit theorem. But basically, the larger the sample, the more it becomes normalized regardless. Like, this was the original, but the more the sample was, the larger the n, the more normalized the curve becomes.
And that makes sense, but why does it have to be 10%? Is that just like, over like a long time of just taking samples 10%?
Yes.
Like the standard rule?
Yes.
That screenshot.
Yes. Yeah, it's terrible. And then me zooming in did not make it any better. It did not. Okay. Let's go to part B. What's changed? What's changed in part B?
The mean height, and the population size is changed, not the sample size.
Sample size has changed. Literally just one person. And so our sample, and hence why I was pointing that out the other day. So our sample size was just one person. And again, in order to use the formulas we're trying to use, we have to say the population is at least times bigger than the sample. So our sample was 1. 1 times 10 is 10. So surely there are at least 10 young women. So now we actually have to check it. So on while, if there's only 1, they don't expect you to probably check it. On part B, you probably should show your work to check it. So 10 times 10 is 100. Can we assume our population is at least 100?
I mean, what counts as a young woman? How young is young?
So we're going to say there are at least, again, if we were doing our people in our classroom and we had a sample, there's only 13 people in here, then that's not 100. So we wouldn't be able to assume the things we're trying to assume and do the math we're trying to do.
So basically, it has to be a certain population, like a certain amount of people for it to be accurate?
Yes. Yes. So if we just had our normal 13 people, we wouldn't be able to do part B. Part A, we're cool because 10 is smaller than 13. But part B, we're not cool because we are nowhere near 100. That's back to, it says, I need to not call it that. You're right, Louise. I need to not call it that. They call it the 10% condition. And it's the fact that this population has to be 10 times, like population divided by 10 has to be bigger than your sample.
So it should be divided rather than multiplied?
We don't know the population, right? So that's why we multiply. So it's the sample we're taking times 10. So n times 10, which for us it was 10. So 10 times 10, and we got 100. And then we think about who is the population we're referring to. And it's all young women. So that's why we're cool and we'll say something smart like there are at least 100 young women. Something smart about how we did check this in order to assume normality. And in order to apply, well, we're not even assuming normality, in order to apply the formulas we want to use, we have to show that first. Okay, and I'm out of room, don't know about y'all, so I'm going to have to show this on a different paper. Okay, so I left that up there. So we had 10 women in our sample. We still have that 64.5. So we need to, the last problem we didn't actually calculate this. In the last problem we had, so we know the 64.5. We know the 2.5. And just like the problem before, we've still got that 66.5. Now, if only we were smart enough to put letters with each of these. I know this is standard deviation, but is the standard deviation of the sample or is the standard deviation of the population? Okay, so standard deviation of the population, what letter of the alphabet or Greek letter should I use?
Oh.
Which looks like that cursive P. Perfect. What letter should I use for the 64.5? I know Jana's drawer does, top drawer first. And then the 66.5 would be
66.5, is that not the M? No.
I mean, I'm cool with that. I'm cool with calling it that. We're wanting to know that it exceeds 60. I'm cool with that. Okay, but on the last problem, we didn't actually calculate this. Why is that?
So we assume us. We assume we done population. Because the number was 1. So you divide it through
Okay,
1 is the same number.
so in part A, we didn't actually calculate this. We actually just used the 2.5. And it's not that we were being lazy. It's literally because if we had plugged it in, we would have done 2.5 over the square root of 1, which would have just been 2.5. So that's why on part A we were too lazy to show this. So if you want to add this to your part A, you can. But I didn't show it because I was being too lazy. But I just now realize why, again, I see why that would help somebody who's still just trying to understand what the crap Miss Compton is saying. Okay, so but for part B, we actually have to calculate this because it's still the 2.5 in the numerator, but our sample size isn't just 1, it's 10, which means it's going to change this number for our standard deviation. So we actually do have to calculate it this time. When you calculate it, what do you get?
0.79.
God bless you, Hunter.
All calculator was right at something.
How did they go?
Okay. Again, the whole problem said to assume normal. So we're assuming normal. So I'm going to change it to z-scores. Do you have to change it to z-scores? No, you don't. Again, you can be like, we're going to do 122. So I would have done this. But the thing that changes is in my denominator, instead of doing the 2.5, since our sample is 10, I'm doing the 0.5.
Wait, so is that a normalized standard deviation now?
Yes.
So I would have to change it to the 0.79.
So in Hunter is doing the normal CDF in his calculator. He's trying to set the lower, the upper, the mean, and the standard deviation. He's still going to do the lower of 66.5, the upper with a bunch of zeros, the mean of 64.5, but for his standard deviation, instead of doing 2.5, he needs to do the 0.79.
Okay.
But again, the whole reason this changed from part A to part B is because our sample changed from 1 to 10. Whew, Lord.
Okay. So do I need to change more things or is that all?
No, that's all you have to change. Okay, when you do this, I get a Z of 2.53, which again, I like Z-scores. When I see 2.53 and I see how large that is and how many standard deviations away from the mean that is, that helps me know I'm going to have a teeny tiny percentage. That helps me. If that doesn't help you and you don't want to think things through like that, that's fine. I like to draw a picture at least so they know I'm not crazy. So if you don't want to draw a picture that's got the normal Z-score of the Z-curve with the 2.53 and I'm trying to find above, you could do Hunter's thing where it's the mean of 64.5, 66.5, and I'm trying to find above that. Regardless, I like to draw myself a picture. It's just a personal thing, and I think in the long run, it shows you kind of understand more, especially if Hunter has a moment where he just puts numbers in commas. Again, they don't like that because they don't know you know what you're doing. Okay, but anyway, I did all this math, and I got a very small percentage. Did you get a very small percentage?
I did.
It was 0.001.
6.
I got 0.0057.
Well, I got 5, 6, but I rounded.
There's a less than 1% chance that if we sample 10 young women that their height will exceed, the mean height will exceed. Did I just put words together right?
No, I mean, yes, let's rephrase. You put words together. No. No. Yes, that's what I needed to say. Like, your words almost match me, like, on the same page. I said there is a less than 1% chance. I was just so proud, Kenzie. It wouldn't come out right.
No.
I was so proud.
My heart dropped for you when she said that.
There's a less than 1% chance that we
The what?
would choose
I
what?
found out today that there were like 9 more people signed up for AP Stats, but they had theater tech last period, and that's the only theater tech class, so they dropped it.
I don't know.
So
Yeah, originally there were 25.
yeah, things always work out behind.
It would have been a no. Again, the larger the sample size, the better the normalized curve goes, but it's okay. There's less than 1% chance that we would choose an SRS of 10 young women whose average height exceeds. That's basically what you said. Oh my God, Kenzie, that was genius. Okay.
She said, no, my God, that was
Well, I was no because it was so impressive. Like I was just so. Someone did math today that wasn't me, and it sounded smart. Like Miracles, people. Miracles.
My stats career.
Oh, wait,
No, I'm gonna tell you.
Kelly?
Wait, what?
Yeah.
Kelly was it Kelly?
Okay.
Oh,
No,
it's
it's
Kenzie.
Kelsey.
Kelsey, yeah. It was with a K. Not a K.
Okay, and then part C, and we're done with this, and I'll let you talk about whatever it is you're talking about. Comment on the differences in the answers that you found in part A and part B. Why is part B less than part A?
You decrease
So B is less than A because
You increase sample size, therefore you decrease you increase sample size, therefore you decrease standard deviation. Yes.
mhm.
Whose jacket is this?
Mhm.
I don't know. That was too long. You don't know who did.
It was right here.
Makes sense. Okay. You increase population, you decrease standard deviation, and therefore
Sample size.
decreasing the per second.
Well, my answers on the AP test are not going to include smart words like therefore.
Wherefore art thou Romeo?
Ew, why'd you say it like that?
Quoted it correctly.
Okay, I liked it. He said part B is less than part A because we increase the sample size, which decreases standard deviation. And in math, if you get really lazy, that little triangle dot thing means therefore, and I'm lazy. So therefore, decreasing the percentage.
Wait, what does that mean?
Therefore,
Oh.
if you put 3 dots like that, it means therefore.
I
Just like ST means such that. There are shorthand ways in math. Yeah,
Do you think I could write an entire answer out just in symbols?
yeah. Or like that one can be such that, or includes like there's tons of ways to shorthand stuff in math class.
A
like another language.
ST
Yes.
down.
And then when you're done with the proof at the end, you know you can put a little box or Q or
Down.
QED.
Boom, done.
Howdy. Okay.
That way people know
So
you're
is
done.
Is that regular shorthand or math shorthand?
Math shorthand, it shows you're a math person. It shows you can do math things.
Okay.
I wish I could write shorthand.
It's really cool.
My
So-
grandma can write instructions.
But the long story short is the fact that he referenced the fact, which is what Jackson asked about 2 days ago and then he tuned out on me for.
I fell asleep.
If the sample size increases, the standard deviation decreases, which is perfect. If the standard deviation decreases, when we figure out the z-score, aren't we dividing by the standard deviation? So if the standard deviation is smaller, that means it's an even more reliable z-score, so the percentage is even more accurate. So one would think larger the sample size, the better. But again, as we've learned today, there's too large of a sample size. Like in this class of 13, we wouldn't be able to do part B because we have to have at least 10% more in the population. So stats is so cool. Okay, tomorrow we will do